Hi, my name is Anastasios Nanos. I'm from Nobificus, and I'm going to talk about VAccel, a framework we're building for interoperable hardware acceleration for applications. We're going to talk about serverless computing, give an overview of what hardware acceleration looks like in cloud environments. Then we're going to talk about our framework, and we're going to show you a short demo. First, let's talk about who we are. We're a small research company based in the UK and Greece. We have a diverse academic and industry background. We've worked for several companies around the world. We focus on the system software, on virtualization, hypervisors, unikernels. We look into hardware acceleration, especially the part of systems integration. And we also look into container runtimes and how to glue these two things together. Get them working on a higher level orchestration framework. So serverless computing essentially is infrastructure orchestration managed by the service provider. It offers effortless scaling, allows the user to focus on business logic and deploy their code without provisioning the infrastructure. Serverless computing frameworks are often deployed in cloud infrastructure. However, some of the use cases are useful for edge workloads as well. For instance, doing ML inference for fast decision-making at the edge. Currently, serverless computing workloads are backed by containers. So, a serverless computing example is shown in this figure. Users write a function in a high-level language. They pick the event to trigger this function. And the serverless framework handles all the infrastructure-related stuff like instance selection, deployment, scaling, fault tolerance, monitoring, logging, security, and all that stuff. This figure shows an example deployment of a popular open source serverless framework, OpenFaaS, on a Kubernetes cluster. So on the left-hand side, we've got the Kubernetes control plane, where depending on, we have a runtime class, the generic runtime class, the container runtime class. The control plane of OpenFaaS is being deployed as generic containers, and these control plane functions trigger, spawn the user functions on the right-hand side, and there's also a gateway endpoint where upon a trigger, the OpenFaaS control plane spawns a new function or scales a new function and stuff like that. Now, the issue in this mode of execution is that since the function workloads are backed by containers, what happens with multi-tenancy in terms of security, of data leaks? Cloud providers at the moment offer their services as a managed service, so they deploy this framework on isolated infrastructure per tenant, so there's no multi-tenancy. However, they have to over-provision the infrastructure. Another solution is to sandbox containers using VMs. So by using hardware extensions, cloud providers are able to isolate workloads. So there's no issue with multi-tenancy there. However, VMs, in terms of accelerator device access and sharing, offer a really complicated set of solutions. In terms of flexibility of the performance of the final execution, and in terms of security. So at the moment, what the vendors of acceleration devices offer for sharing, for device access for VMs, is first do device pass-through. So you assign the whole device to the VM. This is single tenancy. And you can time share with the rest of the tenants on the platform. There's also a mediated pass-through mode where you need to have support on the hardware. There's limited hardware available for mediated pass-through. There's also you also have to have host software support in order to configure the partition of the device, and also some driver support in the guest. Another solution is paravirtualization, which sounds easy, but requires vendor support both on the host and in the guest. So you have to have a custom driver for the VM that exposes a virtual GPU and then interact using the classic software stack, the generic software stack from the VM with the virtual GPU and then with the host and stuff like that. A final solution is using API remoting. So one great example is Arcuda, where Arcuda has a client and server mode of execution. The server runs on the device that hosts the accelerator. The client runs on the VM or on some remote host. The client intercepts and forwards all lower level calls to the server. So, for instance, if you've got a CUDA memcopy or CUDA malloc call, this is being transferred over the network to the server and gets executed there. We were thinking regarding these options that are available for hardware acceleration on serverless. What do we actually need for a workload to access accelerators? For example, in a serverless function for image classification, the user would need to provide the input and specify the model for the classification and the parameters, the accuracy, for instance. So, no need for low-level CUDA calls, no need for complicated drivers, virtual GPUs, PCI, support for hypervisors, stuff like that. So we built VAccel. What we actually do is that we decouple the function call from its hardware-specific implementation. VAccel is a library framework. The user calls a VAccel function, an API function, and VAccel uses plugins to map this function call at runtime to an existing hardware-specific implementation. In this figure, we show the software stack, the full software stack of VAccel. So on the top part is the user-facing API. At the moment, we have image inference API. We have the BLAS, a subset of the BLAS framework as API calls. We have a small subset of TensorFlow. And we also have a user extensible API mode, which we will talk about later. Then the core runtime is actually a simple dispatcher that maps API calls to the plugins, which is the core of the VAccel-framework. The plugins are the glue code between the API calls and the hardware-specific implementation shown in the libraries row here. So the libraries and the hardware, of course, are external to the VAccel software stack. VAccel features, as mentioned, a static API and a user-defined API. So we have some common popular functions available and an abstract mechanism to define custom functions. We have plugins, which are the glue code that implements the mapping of the API functions to their hardware implementation, a simple dispatcher to map API calls to plugins, and some custom virtual plugins to support VM execution. Let's have a closer look at how the software stack interacts with the rest of the components. Now, the core VAccel framework is the dispatcher, the multiplexer that maps API calls to plugins. Let's get an example for the image inference subset of the API. We've got defined some functions defined: image classify, image segment, object detect, etc. And we have a set of plugins that implement these API functions, these API operations. When we say implement, we mean the glue code for mapping these API calls on top to their relevant hardware-specific implementations. So the JSON inference plugin, for instance, calls the generic JSON inference API calls offered from this NVIDIA example repo. The TensorFlow image inference plugin calls a TensorFlow program that implements image inference on TensorFlow using TensorFlow and all the relevant dependent libraries, etc. The NPU image inference, for instance, calls the specific custom implementation on an AM Logic CADAS Vim3 chip that does image inference. Now, an application binary calling VAccel image classify, the VAccel API call for image classification, all it has to do is link against this library and specify at runtime which plugin they need to use. So, an image classification operation request is being issued from the binary application. It gets into the multiplexer. The multiplexer looks up which plugin implements this API call. It's the JSON inference plugin, and then this plugin actually calls the image classification operation that will be executed on the hardware itself. Now, a same application binary, by specifying at runtime a different plugin, can be used to execute on a different hardware device. So the same application binary, VAccel image classify, through the multiplexer and by defining a different plugin, the NPU inference plugin, can be executed on the AM Logic chip. And of course, there's compatibility between architectures. So the same application binary can be executed, provided the relevant hardware implementation honors the API call and the definition of the function. Another example is to use another API called the pose estimate, which is implemented from the JSON inference plugin and the JSON inference framework. Now, that's fine for applications that we implement from scratch on the framework. What happens with existing applications? So let's say we have some code that performs some operation. How do we run it on VAccel? To facilitate this operation, we have built a user extensible API, the generic operation, and some wrapper functions to facilitate the porting of applications. So the rationale is shown in these 2-3 slides. So let's assume we have an application that does image classification through TensorFlow. We split the application into a shared object and the actual function call. So on the red box, we have a shared object that contains all the TensorFlow related functions from this application. And on the green box, we just have a function call that calls the symbol that is exported from this shared object. To port it to VAccel, the only thing needed is to pack the arguments on the user-facing side on a mode that VAccel understands. So we have a specific manner to do that. We have some macros to do that. And on the bottom side, we need to unpack. We need to do the reverse operation. We need to unpack these arguments and issue the function call. It's pretty much remote process execution. Now, how do VMs fit in this execution mode? We have built plugins that run on a VM and forward requests to another VAccel instance library running on the host. So an example is shown in this figure. On the left-hand side, we've got the VM. On the right-hand side, we've got the host. Now we have built a backend for two popular VMMs, two popular hypervisors, AWS Firecracker and Kemu. and the relevant front end, the virtio module, injected on the VM kernel. So using a custom plugin we call the set of virtio plugins, where we implement the whole set of the API calls of VAccel plus the generic operation. We're able to run any application from a VM and use the hardware acceleration part on the host without the VM having any kind of access to the hardware accelerator. Now, because porting, adding a new device to hypervisors is not an easy task, and we're not going to get it upstream. It's too hard to get it upstream on hypervisors, and maintaining custom VMM branches is kind of hard to do. We also added a vsock implementation. So we've got a virtio plugin over vsock, which is a common framework used by VMMs to talk to the host. And we built a simple user space application, the VAccel agent, that runs on the host and intercepts the calls from originating from the VM and calls then VAccel API calls directly on the host. So, in order to use this framework on a serverless framework, we needed to port VAccel to some kind of container runtime. We chose Kata containers because Kata containers offer the sandboxing of containers into VMs. So we ported VAccel to Kata containers. It's a downstream branch, it's not upstream yet. And we have two modes of operation. The first one is using the virtio plugin, where we just replace the hypervisor binary offered by the Kata distribution. And the second mode is that we patched the Kata containers runtime with some logic to spawn the VAccel agent alongside the sandbox of the container. So for every sandbox container, we've got a VAccel agent running on the host, intercepting VAccel calls and doing the actual hardware acceleration execution. To glue all these things together, we deployed an OpenFaaS serverless installation on a Kubernetes cluster using a custom container runtime, using our custom container runtime of Kata that supports VAccel. So we kept the control plane on the generic container runtime, on runC, on the generic runtime class, but we added a new runtime class and the new OpenFaaS profile for functions that need to use GPUs or hardware acceleration in general. So we are able to spawn, to create OpenFaaS functions and spawn custom sandbox containers that are able to use hardware acceleration without direct access to the hardware. Now, the core framework of VAccel is written in C. The plugin system, that includes the plugin system and all the dispatching logic. The plugins are written in C, C++, we have a custom Rust plugin. Anything that can be linked as a shared object could be used as a VAccel plugin. We have bindings for C, for Rust, and we're working on getting the full set of VAccel API in Python. And we also have the VAccel agent written in Rust. We have some wrapper functions and macros available for the GenOp API call, so that existing applications can be easily use VAccel for hardware acceleration. We've got system support for AWS Firecracker. We've got custom virtio backend. Of course, vsock is supported out of the box. The same stands for QEMU. We have a custom virtio backend. and vsock is supported out of the box. Regarding orchestration and serverless and container runtimes, we've got support for Kubernetes, Kata containers, and we've tried OpenFaaS. We plan to try Knative, something more closely, tightly integrated to Kubernetes. And we also have support for unikernels, so we're able to run any VAccel application on top of Unicraft and on top of RampRun. However, given that virtio support is not that up to date on both these frameworks, we're working on getting some vsock support, some proper virtio support on both frameworks. We're also looking into OSV, but we haven't got any progress there yet. Regarding hardware support, we've tried several acceleration frameworks. We've tried Jetson Inference, TensorFlow. We're working on getting PyTorch up and running. We've tried TensorRT, OpenVINO, low-level calls also, OpenCL and CUDA. We've tried several hardware devices ranging from data center GPUs like T4, NVIDIA T4, NVIDIA RTX, some edge GPUs, mostly on Jetson Nano and Jetson Xavier series of devices. And we've also tried some edge TPUs and NPUs like the Intel Neural Compute Stick on Raspberry Pis, on Jetsons, on x86 machines. We tried Google Coral, both the mini and the generic dev board. And we've also tried the AM Logic chip on the CADAS Vim3 device. A short performance evaluation regarding the image classification operation. So we've run an experiment using a Jetson Inference, a TensorFlow program that does image inference written in Rust and C, and an OpenVINO inference example from the samples of OpenVINO written in OpenCL. The setup is QEMU and AWS Firecracker VMs. We've got both virtio and vsock plugins, an NVIDIA RTX 2060 on an AMD host. The OpenVINO is run on the Intel Neural Compute Stick on an Intel NUC i5, and the ARM experiment is run on an NVIDIA Jetson Xavier, and both using the GPU and the Intel Neural Compute Stick. So this is the execution time normalized to native. So the x-axis shows the normalized time. 1 is native. Anything above 1 is the overhead by our framework. The light bars show the virtio plugin, so the one with the patched hypervisor, and the gray bars show the vsock plugin, the execution over sockets. On the first 3 set of bars refer to the x86 case. The next 3 set of bars refer to the ARM64 case. The VM execution refers to AWS Firecracker, so we can see in general that the overhead is negligible. If you see the only outlier is the vsock option for the Jetson Inference classify on the ARM case, which does not exceed 10%, but everything else does not exceed 5%. So we can safely say that we can run image classification from a VM or running on an x86 host or an ARM host using VAccel with less than 5% overhead. Now, to sum up, hardware acceleration on serverless is really tricky. We built VAccel to semantically expose acceleratable functions to serverless workloads. It is a framework that is work in progress. It is open source. It's partially funded by EU research projects. And you can find more information on our GitHub pages. So there's VAccel tutorials, a set of labs that you can clone the repo and run VAccel on your own host, and also the core framework, which is in the VAccel-RT repo. We're happy to answer any questions offline or online, up to you. We have a short demo. We have prepared a short demo, which we will show you right away. Thanks very much.